Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, we're back again, and in this particular lecture, which is lecture 5 of week 5, we're going to investigate the adjustments of the proportional and integral gains in the feedback loop using VEDA simulations. This exercise is intended to give you some intuitive feel for what these gain parameters influence when you're doing contact mode scanning AFM. Very often it's difficult to get this intuition when you're taking data in the lab. Usually there's lots of things going on at the same time. You don't have enough control. But once your instrument is working properly, it is possible to do systematic adjustments of the proportional and integral gain, and the hope is that the simulations will allow you to adjust those gains in a more efficient and appropriate way. By way of reminder from our previous lecture, back I think in week 3 of the course, this AFM feedback loop is sort of the heart of the atomic force microscope. It basically allows you to specify a control law that allows you to minimize the set point force, which you can specify, versus the actual force which the AFM tip measures at any point along a scan when the tip is in contact with the substrate. So this air signal, which I indicate schematically in this diagram, is the difference between a set point force in the position of the substrate with respect to the cantilever, right? That air signal is minimized by these two controllers that operate in parallel. One is the proportional controller, the other is the integral controller, right? The proportional controller produces a signal to the AFM, which is linear in the air signal. The integral portion of the controller sends a signal to the AFM controller, which is the sum of previous airs. And the relative weighting of these two signals is specified by the parameters k sub p and k sub I. In this lecture, those parameters are also called just p and I, sometimes to make it easier to talk about. And the trick is, of course, to adjust those two parameters, k sub p and k sub I, so that the controller, the output to the scanning probe microscope, in other words, the motion of the sample with respect to the tip, right? That motion minimizes the air signal that's specified here in the slide. So lots of ways to do that. There's always an optimal choice for P and I. The question is, how do you achieve that optimal choice? First, let's talk about the feedback warning signs that you should be aware of. In my experience, if the feedback loop is set too slow, in other words, if the P and I parameters are too small, you tend to get blurred images, and you'll also experience tip crashes repeatedly. That's a sure indication that the P and I have to be increased in order to speed up the response of the controller to the motion of the tip. So clearly, if your sample is very rough, if there's a lot of debris on the sample, your P and I controller values have to be increased in order to make the response of the substrate with respect to the tip fast enough to track the motion of the tip over the features. If your feedback is too fast, what you'll tend to see is oscillations in your image. So whenever your tip goes over a sharp feature, you'll see a ringing effect that shows up as a sequence of bright and dark bands. That's usually an indication that your feedback is set too high. You have to back off. There are many ways to set the feedback parameters. Typically, what you tend to do is you tend to set the integral controller to 0, to a very small value, and then you continually increase the proportional gain until you start to observe noticeable oscillations in your image. Now, this adjustment can be made while your AFM is scanning over the substrate. So it's like every second or third line in a data acquisition mode, you can readjust the proportional gain, and eventually you'll start to see oscillations set in. When you see those oscillations set in, then you just note the value of the proportional gain that you've set. Take a fraction of it, something on the order of 2/3 of that setting, and that would then be the optimal proportional gain for the particular tip and the particular substrate that you're trying to scan. Once you've got this proportional gain set, then you slowly increase the integral gain. You continue to increase the integral gain while you're scanning, right, as you're acquiring an image. And what you're looking for is you're looking for a hint of an oscillation in the image. This hint of an oscillation starts to show up as a graininess in the image itself. And when you see that graininess first appear, that's when you stop adjusting the integral gain. And many times this procedure then allows you to rapidly achieve values of the proportional and integral gain that are optimal for the sample that you're trying to scan. So it's kind of useful to run through some VEDA simulations to illustrate these points that I tried to make in a very general way. So let's do a few examples and see what we can learn from those simulations. So the first example I like to run through is I like to consider a step in a sample. The height of the step is 30 nanometers. The length of the step is 50 nanometers. Clearly, these parameters can be adjusted to match the sample of interest in your particular case. I'm going to, in this case, choose a rather stiff cantilever, 3 newtons per meter. Usually, when you do AFM scans, you use cantilevers that are not quite so stiff. My set point deflection is going to be 2 nanometers, which means that my set point force is 6 nanonewtons. In this particular example, I'm going to investigate the changes in the proportional and integral gain, and I'm going to try to do it in a systematic way so that I can see the effects of the substrate motion as the tip tries to respond with different values for P and I. So the results of the simulations that I've done, I've selected 3 gain settings for P and I. One is too low, it's 0.002. One is too high, that's 0.007. And maybe the optimal gain is a value on the order of 0.04, 0.05. Right? And I plot out the response of the Z piezo as the tip encounters this step-like feature. The geometry of the step-like feature is plotted in red in this particular slide, and the various responses of the Z piezo as the tip scans over the sample are plotted in blue. So you can see that when the gain is set too low, the tip responds too slowly to the sharp step, and then when the tip loses contact with that sharp step, right, there's a parachuting effect. The tip drifts down to the flat substrate. It requires a certain length of time for that to occur. When the gain is set too high at 0.007, what you'll find is that the tip overreacts to the sharp increase in the geometry, in the topography, so that initial step height of 30 nanometers, the tip overshoots that by quite a bit before it recovers and settles down. On the trailing edge of the feature, you can see that the tip reacts much more quickly now to the feature, to the drop off of the feature. So the parachuting of the tip off the feature is much faster now than it was when the gain settings were at 0.002. In VEDA, you can plot things like the mean interaction force as the tip scans over the substrate. So I just illustrate the mean interaction forces here as a function of the scan direction. Note that at x equals 0 on this plot, the mean interaction force is 6 nanonewtons. Of course, that's the value that we specified by specifying the spring constant and the deflection, the set point deflection of the cantilever. So when the mean interaction force is at 6 nanonewtons, that means that the controller is perfectly tracking features in the substrate. When the mean interaction force deviates from that 6 nanonewton set point force, that indicates that we're making errors in our estimation of the topography. And you can see that the mean interaction force shoots up quite a bit when the tip first encounters this step. And then when the tip parachutes off the step, the mean interaction force goes to 0. It actually drops down to 0. That just means the tip's not in contact with anything, so the deflection of the tip is 0. Deflection of the tip is 0. That means the mean interaction force between the tip and the substrate is essentially 0. And it's pretty clear that when the gain settings are 0.002, the long time it takes for the tip to parachute off this step-like feature is illustrated by this long region in the where the mean interaction force is equal to 0. So just an example of the types of plots you can get out of VEDA simulation. There's about a half a dozen different options for you to choose. And the lectures that have led up to week 5 should allow you to understand in a pretty straightforward way the different plots that you can obtain with the VEDA simulation tool. I always like to turn the tip dilation on by clicking this geometric convolution box. This is under the simulation parameter tab. So I just do that in this case to show you if you include the finite radius of the tip, what the geometry of the substrate appears to be based on the motion of the sample with respect to the tip. So again, the red line indicates the geometry, the geometrical feature that we've specified. The blue line shows how the tip responds when the radius of the tip is included. So the blue line calculation, again, is going to require a few minutes to complete because it's constantly adjusting, because it has to properly take into account the tip radius. The next slide here, just I try to make a systematic study of how the proportional and integral gains influence the geometry that you would get in an AFM scan. So in the first on the left-hand region of this slide, I investigate the case where the integral gain is essentially set to 0. In practice, I didn't set it to 0. I set it to 0.0008, which is a very small number. I set the proportional gain to 0.005. So essentially, the integral gain is 0, the proportional gain is large. And what you can see is you can see very clearly that the substrate motion with respect to the tip misses pretty severely on both the leading and trailing edge of the feature. So from your AFM image, you might conclude this feature really has a rounded leading edge and it has a long sloping edge if you just blindly believe the image that that the AFM produces. On the other hand, if you set the proportional gain equal to 0 and you make the integral gain 0.005, which is a rather large value in this example, you can see that now the feature that the AFM produces tracks more closely the image of or tracks more closely the actual geometry that we specified. You miss a little bit on the leading edge, you always get that overshoot That seems, that's a generic feature of any AFM image. Unless your feedback is adjusted very well, you tend to have a little bit of overshoot on that leading edge. And in this case, the tip parachutes off the feature rather rapidly. So you would conclude that the feature that you're imaging is a little bit extended on the trailing edge. It does a pretty good job of matching the leading edge. So just an indication of things that you should watch for when you actually do contact mode scanning. And it tries to emphasize the importance of setting the proportional and the integral gains. I'd also like to demonstrate the influence of scan speed for fixed controller gains. So very often you'll go through a long setup procedure where you carefully adjust the proportional and integral gains, and then after a few scans you decide to increase the scan speed so that it doesn't take quite so long to obtain an image from your AFM instrument. That process has to be incorporated with a readjustment of the proportional and integral gains. Because if you don't readjust the proportional and integral gains, if you just increase the scan speed, you're likely to introduce artifacts into your image. And this particular example is intended to try to illustrate that particular case. So again, I list the input parameters that I'm using in this simulation. In this simulation, I'm producing a trench in a solid substrate. The sample has a modulus of 100 gigapascals uniformly throughout the substrate. The depth of the trench is 30 nanometers. In this case, I use a trapezoidal trench geometry. I pick a cantilever stiffness of 0.6 newtons per meter, and my set point deflection is 2 nanometers. So that would, multiplying those two numbers would tell me my set point force is something like 1.2 nanonewtons. And I've got proportional and integral gains set, and what I'm going to do is just vary the scan speed from 2 lines per second to 5 lines per second to 10 lines per second. Initially, I'm not going to turn the tip dilation effects on. So the tip is going to essentially have a 0 radius, but once everything is optimized, then I can go back and click that geometric convolution box, turn on the tip radius, and see what the actual scan of, what the actual topography, the AFM scan would tell me for this particular trapezoidal trench. So first slide here just shows for the constant P and I values that I specified in the previous slide. It just shows you the images that, or just shows you the motion of the substrate with respect to the tip as a function of scanning speed. So what you can see is that for scanning speeds that are on the order of 2 lines per second, the AFM tip reasonably well tracks the features in the substrate. However, if the scan speed is increased up to 10 lines per second, you start to make gross errors in the estimate of the feature, right? In fact, you would misinterpret the structure of the feature altogether. The topography of the feature would be completely wrong if you just relied on that 10 line per second image, right? You would miss the depth of the feature, and you would conclude that instead of having a trapezoidal feature present, you've actually got some sort of a triangular feature that's there. In this example, I choose the 5 line per second scan speed. Now I systematically adjust the proportional and integral gain, and you can see that by adjusting P and I in a rational way, you can actually find an optimal scan, optimal feedback parameters that does a reasonably good job of reproducing the topography of this trench-like feature. On the other hand, if your proportional and integral gains are set completely wrong, the case for the solid blue line in this slide, right? Again, you're going to misinterpret the geometry of the feature. Your AFM image would not even come close to reproducing that trapezoidal topography. So again, this is something that you have to worry about. You have to systematically adjust these parameters. And in my opinion, doing this adjustment in VEDA before you go and do an experiment gives you a sense of what sort of things you would have to look for. So, you know, you have to combine your understanding of the substrate you're scanning. You have to have some appreciation of the features in the substrate that you're trying to image. And you have to couple that with the scan speed and the feedback parameters. And hopefully these examples illustrate those effects. So the last slide in this particular lecture, I just turn on this geometric convolution effect. So I let the tip radius come into play. So this is done to illustrate what a realistic image would look like. So in this case, the solid blue line represents the case when the tip radius is 0, right? The solid blue line does roughly reproduce the topography that we specified. The topography we specified is the red curve. You certainly get the depth of the feature correct. You would misinterpret the leading edge, and so it would be difficult for you perhaps to estimate accurately the width of the feature. The situation gets much worse when you turn on the tip dilation effect. So in this particular example, I've got a tip dilation of about I've got a tip radius of 5 nanometers, which is a reasonably sharp tip. And you can see that the light blue curve in this particular simulation really shows up as a triangular divot, a triangular wedge in the substrate. It's not even close to the trapezoidal feature that we specified. So just again an illustration of how you can go wrong when you're doing contact mode AFM on trying to measure features that are etched into a substrate. So that's, I think, all I wanted to say about the proportional and integral gains. Hopefully this discussion will provide some motivation for you to go into VEDA and try some simulations based on features that maybe are more interest to your particular research application. I just wanted to say that the next lecture is going to be just a general discussion of tips and tip artifacts. We'll provide a variety of different insights that we've gained over the years here using tips to scan samples, and we'll see you for that lecture in a short period of time. So thanks for your attention.